An eye tracker does not read minds. It does something more interesting. It measures light reflected from the eye and uses that geometry to reconstruct gaze direction. Hundreds and sometimes thousands of times per second. What we eventually see on screen is a gaze point, a scan path, or an impressive heat map. But these images are only the end of a much longer measurement chain. Before them come infrared illumination, an eye model, calibration, filters, and analytical decisions. In this video, we will move from a single corneal reflection to metrics such as time to first fixation, dwell time, and pupil diameter. We will also see why two studies with similar heat maps can lead to completely different conclusions. Most professional eye trackers use near-infrared light and the PCCR method, pupil center corneal reflection. Illuminators direct light at the eye that remains invisible to the participant. Cameras record the pupil and one or more bright reflections on the cornea, commonly called glints. The algorithm is not searching the image for thoughts or attention. It is searching for geometry. It locates the pupil center, the corneal reflections, the spatial position of the eye, and the gaze vector. Modern systems use multiple illuminators and a three-dimensional eye model, allowing them to compensate for natural head movement within the permitted tracking area. The vector alone does not tell us which pixel the participant is viewing. Calibration is required. The participant looks at targets with known positions, while the system learns the individual relationship between eye geometry and screen coordinates. Calibration should be followed by validation, an independent measurement of the remaining error. Without it, an impressive visualization may look credible even when every gaze point is systematically displaced. Eye tracking quality involves at least 4 separate concepts. The first is accuracy, the distance between where the participant is actually looking and the point recorded by the device. The second is precision, the spread of consecutive samples while gaze remains on the same location. A system may have high precision but poor accuracy. The sample cluster is tight, but it lands away from the target. The opposite is also possible. The average falls on the target, while individual samples are noisy and widely dispersed. Both parameters are normally expressed in degrees of visual angle. For intuition, half a degree at a viewing distance of 65 centimeters corresponds to roughly 6 millimeters on a flat screen. This is simply geometry, but it shows the scale of the problem. For a large button, the difference may be irrelevant. When analyzing individual words, icons, or micro saccades, it becomes critical. We must also consider data loss, trackability across different participants, latency, and synchronization stability. Sampling frequency matters, but the number of hertz alone does not describe the quality of the complete system. Gaze does not move across a scene like a smooth camera pan. We obtain most visual information during fixations, short periods of relative stability. Between them are saccades, extremely rapid gaze shifts that often last only a few tens of milliseconds. We can also measure smooth pursuit of a moving object, micro saccades, blinks, binocular vergence, and changes in pupil diameter. The eye tracker itself stores samples. A classification algorithm then decides which parts of the signal will be labeled as fixations and which as saccades. Velocity thresholds, filters, and the handling of missing data all affect the result. 60 Hz is sufficient for many fixation-based analyses of visual attention. But if we want to measure the shape of a saccade, its onset, offset, and peak velocity, a practical minimum is usually around 200 Hz. The precise threshold depends on the algorithm and the research question. Tobii Pro Spark is therefore not intended for detailed saccade dynamics, even though it records fixations effectively. Successive fixations connected by saccades form a scan path. Circle size may represent fixation duration, while connecting lines preserve the order of transitions. That distinction matters. A scan path preserves sequence. A heat map usually removes it. In mobile studies, Tobii ProLab can also import movement-compensated fixations, making replay more representative when both the participant and the scene are moving. A fixation is not proof of preference, understanding, or purchase intention. It means that gaze was directed towards a particular area. Interpretation must be grounded in the research question, the participant's task, and the remaining evidence. Sampling frequency describes how many times per second the system records eye position. 60 Hz means one sample every 16.67 milliseconds. 250 Hz means one every 4 milliseconds. 1200 Hz means one every 0.83 milliseconds. If we are studying general visual attention on a website or package, 60 Hz may be entirely sufficient. If we need the precise onset and offset of a rapid saccade, or want to analyze microsaccades, reading or brief experimental events, we need denser sampling and low noise. In the animation, the gray curve represents the true eye movement. The colored dots are recorded samples. A slower tracker captures the beginning and the end, but reconstructs the dynamics between them poorly. A faster system gives a better estimate of both the movement profile and event timing. The rule is not simply that more hertz is always better. The choice should follow the duration of the phenomenon, required accuracy, number of observations, synchronization needs, and data budget. Start with the research question, then choose the frequency. After recording the data, we define areas of interest, or AOIs. An area may be a face, logo, price, button, or individual interface component. Only then do raw coordinates become metrics that answer a specific question. Time to first fixation describes how quickly an area was noticed after the stimulus began. For a defined interval, this is one fixed value, not a counter that keeps changing over time. Dwell time describes the total time spent looking within the area, according to the definition used in the analysis. Fixation count may indicate the intensity of exploration. Revisits show how often a participant returned. The proportion of participants entering an AOI describes its reach. A transition matrix reveals order, for example, face, product, shelf, and product again. Event definitions must also be distinguished. A visit usually covers the interval from the first to the last fixation within an AOI. A glance may also include the entry saccade. Terminology depends on the software and fixation filter, so the definition must always be stated in the report. With a dynamic stimulus, such as video, time bins divide the analysis into intervals and reveal when an area was visible and when it was viewed. Every results table should also include data quality, the proportion of valid samples, periods of signal loss, and calibration performance. Without these values, it is easy to confuse participant behavior with measurement quality. In screen-based studies, coordinates are mapped to a stable stimulus. With wearable glasses, gaze must be placed within the scene camera video and dynamic objects tracked over time. This is a more difficult problem, but it allows researchers to study a shop, sport, cockpit, or workplace in its natural context. A heat map is an excellent communication tool, but it is easy to assign it too much meaning. Color is not the temperature of attention. It is the result of aggregation, smoothing, and the chosen scale. Changing the smoothing radius can alter the appearance of exactly the same underlying data. More importantly, a heat map averages attention across participants and hides chronology. One participant may begin with a face and then move to the price. Another may follow precisely the opposite sequence. Once combined, both participants may produce similar hot areas, even though their behavior was different. A small sample creates unstable islands. A larger sample stabilizes the image, but cannot repair a poorly defined task or low-quality recording. Scanpaths, AOI metrics, participant-level distributions, and uncertainty measures should therefore be reported as separate analyses, not blended into a single picture. The safest conclusion is this. A heat map shows where recorded fixations accumulated under this particular procedure. It does not automatically explain why they occurred, what the participant remembered, or whether they will buy the product. An eye tracker can record much more than a gaze point. Depending on the system, the output may include the position of both eyes, pupil diameter, eye openness, gaze origin, and sometimes head position. Tobii Pro Spark reports pupil diameter, so it is not correct to say that pupillometry is technically impossible with this device. Spark is, however, a single camera system optimized primarily for fixation data. For demanding pupillometry, Profusion and ProSpectrum are preferable. They use 2 cameras and offer higher precision, higher sampling rates, and additional control data, including eye images. Pupillometry is often used as an indirect measure of cognitive effort or arousal. But the pupil responds very strongly to light. A change in screen brightness, gaze angle, or viewing distance can imitate a psychological effect. Stimuli must therefore be controlled, the signal cleaned, and conclusions stated with care. The most complete picture comes from synchronization. Eye tracking tells us where the participant looked. Electrodermal activity can indicate arousal. EEG records electrical activity from the brain, while cardiovascular and respiratory signals describe physiological state. Tobii Pro Lab and the Pro SDK provide software synchronization, while selected devices add hardware inputs. ProSpectrum has an 8-bit TTL input for precise time markers, and Glasses 3 has its own synchronization port. A shared timeline does not turn these measurements into mind reading, but it helps distinguish visual attention from the body's response. Device selection should begin with the environment and the phenomenon, not the largest number in a specification table. Accuracy, precision, tolerance of head movement, participant population, lighting, and synchronization method all matter. Tobii Pro Spark operates at 60 Hz. It is small, lightweight, and powered through a single USB cable, making it easy to use with a laptop in a classroom, at a client site, or in a mobile UX laboratory. A single camera and a 3-dimensional eye model provide strong fixation data with natural head movement. Under optimal conditions, Tobii specifies accuracy of approximately 0.45 degrees and filtered precision of 0.26 degrees RMS. Profusion is available at sampling rates up to 250 Hz. 2 cameras improve precision and tolerance of head movement. The system supports both bright pupil and dark pupil tracking, automatically selecting the mode that produces the best data. Bright pupil mode is available at 60 and 120 Hz. This helps reduce data loss in diverse populations, including participants wearing corrective glasses or presenting more difficult eye geometry. Under optimal conditions, the specification gives accuracy of 0.3 degrees and filtered precision of 0.04 degrees RMS. Pro Spectrum is designed for demanding neuroscience, reading research, micro saccades, and rapid eye movements. It records up to 1,200 samples per second, while 2 cameras maintain high data quality during natural head movement. Here, every number must be read together with its test condition. Median accuracy is approximately 0.3 degrees with a supported head and 0.43 degrees with free head movement. Filtered precision is approximately 0.01 and 0.02 degrees RMS, respectively. Spectrum does not remove the need for a chin rest from every protocol, but it gives the researcher much greater freedom in study design. When participants need to walk, work, or select products from a shelf, wearable eye tracking is required. Tobii Pro Glasses 3 operate at 50 or 100 Hz and use 4 eye tracking sensors. Their design preserves a wide, unobstructed field of view. Clear protective lenses and infrared blocking tinted lenses are available for bright outdoor conditions. Tobii specifies accuracy of 0.6 degrees, but precision in motion depends on activity, fit, and frame slippage. These values must not be compared without their footnotes. Optimal conditions, filtering, head support, and stimulus type all affect the result. The comparison table is a starting point, not a device ranking. The core of the ecosystem is Tobii Pro Lab. In a single environment, researchers can design an experiment, present stimuli, perform calibration and recording, define AOIs and time bins, analyze fixations, and export data. In mobile studies, ProLab can use movement-compensated fixations. In multimodal projects, it aligns events on a shared timeline. ProLab also supports distributed online research. Participants take part remotely, using their own webcams, complete self-calibration, and the researcher analyses AOI results in the same workflow. Tobii Sticky is a related but separate webcam eye tracking platform for consumer research, advertising, packaging, websites, and video. These 2 solutions should not be confused. Only after we have considered the phenomenon, environment, required error, timing, and software should we select the eye tracker. Eye tracking is a precise measurement method, but its value does not come from an impressive dot on a screen. It comes from correct calibration, quality control, appropriate sampling, and metrics selected for the hypothesis. First, define the phenomenon and the timescale on which it occurs. Then define the research environment, participants, and acceptable error. Only then select the eye tracker. Interlab is a distributor of Tobii solutions in Poland and Eastern Europe. We help research teams select screen-based or wearable systems, software, and synchronization with physiological instrumentation. More educational materials and interactive simulators are available from the Interlab Academy.